There's a moment in every machine learning journey when the model, like a young student preparing for an exam, faces a critical fork in the road. Will it memorize every detail of its textbook, every comma, every anomaly, every typo, or will it learn the true principles behind the patterns? This dilemma lies at the heart of two of the most common challenges in training machine learning models: overfitting and underfitting. Let's begin with overfitting. Imagine a student who prepares for a history test by memorizing the textbook word for word. He knows every date, every paragraph, even the misprints. On exam day, the questions are slightly rephrased, and he panics. He can't adapt because he didn't understand the underlying themes, he only learned the surface. That's overfitting. A model that becomes so good at mimicking the training data that it begins to lose touch with reality. It performs exceptionally well on the data it's already seen, but give it something new, and its confidence crumbles. It learned the noise, not the signal. The quirks, not the truths. It doesn't generalize, it memorizes. Overfitting is often the result of a model that is too complex for its own good. Perhaps it has too many parameters, or it's being fed too many features. Perhaps the dataset is small, and the model latches onto random fluctuations as if they were meaningful. The result is a fragile illusion of perfection. Now picture another student. This one barely skims the textbook. He gets the basic idea, that the French Revolution happened, that there was a king and a guillotine, but he doesn't bother with the causes, the nuance, or the timeline. He shows up to the test with a few vague ideas, but nothing sticks. He can't answer the training questions well. He certainly can't handle the test questions. This is underfitting. The model is too simple. It hasn't learned enough from the data to make any meaningful conclusions. It fails to capture the complexity of the patterns it's supposed to recognize. It guesses when it should reason. It assumes when it should analyze. Underfitting happens when the model lacks capacity. Perhaps it's using linear regression to try to model a curving, twisting dataset. Or perhaps it was trained too briefly, or constrained too tightly by regularization or lack of features. It's like asking a child to paint a forest using only one color and one brushstroke. The result is inevitably too crude. In both cases, performance suffers, but for opposite reasons. Overfitting is the trap of excess: too much complexity, too much sensitivity, too little restraint. Underfitting is the trap of simplicity: too little learning, too much assumption, too much indifference to detail. The goal, always, is balance. We aim to build models that generalize, that capture the essence of the training data without becoming enslaved to it. We want them to learn the patterns that matter, and to ignore the ones that don't. We want models that, like wise students, study the textbook for meaning, not just for memory. To avoid overfitting, we might simplify the model, limit its complexity, or introduce regularization techniques that gently penalize it for growing too large. We might gather more data, or cross-validate the results across multiple samples to ensure consistency. To overcome underfitting, we might expand the model's capacity, give it more features to explore, or train it longer so it has time to grasp the structure beneath the surface. In the end, the journey of model training is not unlike the journey of learning itself. We don't want rote memorization, nor shallow generalization. We want understanding. The best models, like the best learners, strike a delicate harmony. They listen, they observe, and then they learn just enough, not too little, not too much, to make sense of the world around them. That is the art of balance in machine learning. And that is how we turn data into wisdom.